How can we validate a statistical model? By validate, I mean determine the quality of the predictions from the model without reference to the original data that was used to train or develop the model. The gold standard would be to collect some new data not used to fit the model and see how well the model performs at predicting the new data. However, this means there's some data that are relevant to the problem that haven't been used, and this seems somewhat wasteful, and in fact it is. A compromise that you might be able to do would be to carry out what's called cross-validation, where the data take turns as both testing points and training points. In k-fold cross-validation, the data are randomly divided into k equally sized parts. Then the model's fitted k times. For each of those k fits, one part of the data are left out, down here, and used to test the model estimated from the other k-1 parts of the data. Then you repeat the process, leaving out each of those k parts in turn until you've generated predictions for all of the observed data. And in each case, the prediction is made using data that is not used to estimate the model. So let's take a look at doing this sort of by hand using the GLM data set of the counts of dickcissels that Andrea Hansen recorded in her field plots. And so what we had in our final model was that dickcissels increased with the visual obstruction reading, and that there was an interaction between the visual obstruction reading and the second principal component of the landscape. And this model here, set to the median values of that second principal component, looks pretty good. But let's find out how good it is. And we're going to do an eightfold cross-validation by hand. So the first step is to divide the data into 8 parts. And there's many ways of doing this. But what we're going to do is first sort the data according to a random number. So we're going to randomly order the data to break up any sequential correlations in the data set. And then, that's what we've done here. And then what we're going to do is we're going to create a vector, we'll call it pick, that's going to have the numbers 1 through 8 in it each 7 times. And now you see why it's easy to choose eightfold cross-validation in this case. There's 56 data points, and so we're going to be able to have each of our folds will have 7 data points in it. And then we can simply say abundances pick equals 3 will pull out 7 of the rows in the data set that have been randomly selected from the data set as a whole. So that's the first step that we need to be able to do in order to do cross-validation. So here's that particular set pulled out in visually in hot pink. And what we can do is we can now fit the model to this to the data not including the hot pink points. And then if we made the same prediction, now what we're doing is using that sequence of visual obstructions and the median values of PC2. We can get that pink line. You'll see that it's slightly different, although not that different, from the original fitted line that used all of the data. But we can go farther. For cross-validation, what we need to do is predict each of the hot pink points using the model that has using that same pale pink line. And there they are there. So those are now the points that predict each, or the predicted points for each of our independent observations. And then we would repeat that process for each of the k pieces of randomly selected data. And that will get tedious, so what we'll do is we will use a loop, a for loop. You might not have seen this structure before. And it's not necessary to learn this particular syntax for this course because there are functions that will do cross-validation for you. But just essentially what this does is going to repeat this block of code 8 times, and in each pass through, this object I will have a different number associated with it. And we create a vector to store our predicted number of dickcissels in each case. So the first thing we do is we fit our generalized linear model using the data without set I. Then we use the predict function together with our fitted model to predict the values for set I. Equals equals I here is different from not equals I. And finally, we store that result into the vector that we created above. So what we can do then is we can plot the observed number of dickcissels against the prediction for each site that is done using independent data. And we can do that for both the cross-validated predictions. So these are independent predictions as if we had collected new data. And here we have the fitted values. So these are with using all of the data to generate the predictions. So these predictions are not independent from the observations, and these ones are. And then we can calculate the residual deviance, that is, how far away is each of these points from the perfect one-to-one line. And the residual deviance of our original model was 93.3, and the residual deviance of the cross-validated predictions is 105.7. So you can see that we've lost a little bit of predictive power by shifting to independent predictions. And this is exactly what we would expect, because these data, the data that are used to generate these predictions, are independent. They weren't part of the original fitted model, and so we would expect there to be a little bit less, a little bit more variance between the predictions and the observations. However, if we use this cross-validated score as a metric of how complex things are, we reduce the risk of overfitting our data sets to the peculiarities of the actual data. And so one might argue that if we focused on the residual deviance, the risk that we run is that as we add more and more parameters, we get a better and better fit. But if we feed in new data, we'll find that those overly complex models then in fact do worse. So that's the idea behind cross-validation, and we'll see it put to use in a number of different places, including generalized additive models and regression trees.